Welcome to the core of computer science. If you're learning to code, you might be asking, why do we need an entire course on data structures and algorithms? Can't we just buy faster computers? Here's a reality check. A standard Python environment can execute roughly 10 million basic operations per second. That sounds incredibly fast. So if we write a program, shouldn't we just measure its speed using a stopwatch? No, stopwatches lie. If you run the exact same code on a supercomputer and a 10-year-old computer, the stopwatch gives you two different times, but the underlying algorithm hasn't changed. To truly judge code, we can't look at seconds. We have to count the total number of structural steps it takes. Let me prove this perfectly in Lecture 1 using the greatest common divisor, or GCD. Let's say we want to find the GCD of two massive numbers. The noob method is brute force. We find all factors of m, find all factors of n, compare the lists, and pick the biggest match. If m and n are a billion, your code steps through a billion numbers. It's slow, exponential, and painful. Why? Let's see. Suppose we want to find GCD of small two-digit number as shown in screen. We first find factors of m, then factors of n, and then we compare and get the GCD. Ta-da! But focus on the number of processes it took to find this GCD. Our computer will give this in a few milliseconds. But hey, what if we increase these digits to three-digit number? It keeps going, and when finally we get, man, look at the number of steps it took to find this. Now hey, what if we have 7-digit or 8-digit number? Our computer will explode. Why? Let's plot a graph. Take x and number of digit and y as number of processes it takes in worst case. See, at x equals 7, we're getting nearly 1 million processes. From milliseconds to seconds. Now what if our input is of 10 digits? Hey, it takes nearly 10 billion processes, which means Python will take 1,000 seconds. That's nearly 16 minutes. See that? No matter what supercomputer you have, if you have non-optimal algorithm, no computer can help you. So brother, what is optimal way to do this? We have another method called subtraction method. So, we upgrade to the subtraction method. The math tells us the GCD of m and n is the same as the GCD of n and m minus n. We just keep subtracting the smaller number from the bigger one, much faster. But wait, what if m is a billion and n is 1? You're subtracting 1 a billion times. You just accidentally created a billion steps again. We don't want that. So, enter Euclid's algorithm, the pro method. Instead of subtracting repeatedly, we use the remainder or modulo. So, let's see some mathematical things. Assume m and n are divisible by d, which means m equals AD and n equals BD. Put this in the equation of division and we will see that d divides the remainder too. Now we divide m by n and just keep the remainder and repeat the process. Even if m is a billion and n is 2, the modulo operation solves it in one single step. See? This is why PDSA matters. Brilliant logic crushes raw computing power every single time. Where billions of processes for 10-digit numbers in brute force method and our new Euclid's algorithm takes roughly 10 processes for same inputs. Now, how do we measure this efficiency? Imagine you write a search algorithm to find a number in an unsorted list. You run it, and boom, the number is in the very first slot. It took exactly one step. Does that mean you wrote an ultra-fast algorithm? No, you just got lucky. This is the best-case scenario. As programmers, we cannot engineer systems based on luck. We also can't rely on the average case, because calculating mathematical averages for every possible data input is incredibly complex. Instead, computer scientists focus strictly on the worst-case scenario. What is the maximum number of steps our code will take if the universe completely turns against us? That worst-case ceiling is what we call Big O. Let's define Big O mathematically. A lot of students get confused here, but it's just an upper boundary. We say that our messy algorithm's time, f of n, is Big O of a clean function, g of n. The formal definition is this: f of n is less than or equal to a constant c multiplied by g of n, for all inputs n greater than a starting point n naught. Look at the graph. When the data is small, our algorithm might behave weirdly, but after a certain point, n naught, the smooth upper bound function completely overtakes it and stays above it forever to infinity. The constant c is just there to account for whether you're running Python or C++ or using a Mac versus a PC. Here's a trick question professors love. Is Big O unique? No. If your algorithm's worst case is bounded by n squared, it is mathematically also bounded by n cubed and n to the fourth. But as engineers, we always want the tightest possible upper bound to accurately describe our code. Now let's look at the standard Big O classes. Remember, Big O doesn't measure seconds, it tracks how the number of steps scales when your data scales. First, O of 1, constant time, the absolute best. No matter if your array has 10 items or a billion items, finding an element by its exact index takes 1 step. Data scaling doesn't affect it. Next is O of log n, logarithmic time. This is the pro method for searching. Instead of checking every item, a binary search cuts the sorted data in half every single step. If you have a billion items, a noob linear search takes a billion steps. Binary search finds it in just 30 steps. Then we have O of n, linear time. If you double your inputs, your steps exactly double. Reading every line of a text file is O of n. It's a 1-to-1 ratio. Next is O of n log n. This is the gold standard for efficient sorting, like merge sort. It's slightly heavier than linear time, but highly scalable for big data. Finally, we reach O of n squared, quadratic time. This is what happens when you write a loop inside a loop. The scaling here is brutal. If you double your inputs, your steps don't double, they multiply by 4. If you triple the number of inputs, processes becomes 9 times. Let's see. Suppose I have 5 friends and 5 notebooks, and I want to check which book's names matches with my friends' names so I can give it to them. Assume not a single book have their name. First, I will check for my friend 1 by checking all 5 books' first page. Then I will check all books again to see which name matches with my friend 2's name. Then same for friend 3, 4, and 5. See how many processes it took me? Nearly 25, which is 5 times 5 steps for simple task. Let's look at a real-world disaster. Imagine you have a database of India's population, roughly 1.4 billion people. You also have a leaked database of 1.4 billion credit cards. You want to write a script to see which person matches which card. Assume the case where there won't be a single card which will match with any one of them. The noob method is to take person number 1 and check them against all 1.4 billion cards. Then take person number 2 and check them against all 1.4 billion cards. This is an n-squared nested loop. Let's do the math. 1.4 billion times 1.4 billion is roughly 1.96 times 10 to the 18th steps. That is 2 quintillion operations. Now let's feed this to our Python engine running at 10 to the 7th operations per second. 2 quintillion steps divided by 10 million steps per second equals 200 billion seconds, which equals over 6,000 years. your computer will literally turn to dust before that script finishes. That is why an n-squared algorithm is unacceptable for big data, and why an n log n pro algorithm is required. But if we go with binary searching, our algorithm will take n log n steps, which will take only 1.18 hours to check this data. See, from 6,000 years to 1 hour, just by some tweaks in code and logic. So before you write a single line of code in PDSA, understand this: algorithm design isn't about memorizing syntax. It is about understanding how math scales over time. You are defining the mathematical boundary of the worst possible scenario and engineering a logic path that escapes it. If this deep dive finally cleared up the confusions around Big O, worst-case scaling, and the GCD proofs, hit that subscribe button. Drop a comment below if you want me to mathematically break down sorting algorithms next. See you in the next one.